2. So it's, yeah. I mean, it's not exactly 5.3 implies 5.2, but that 5.3 implies 5.2 is an immediate consequence of theorem 5.6. All right. He says, we shall use a diagonalization procedure to prove the theorem. It is important to add this technique to one's bag of tricks. Let's see here. All right, well, here goes nothing. Let x sub j, j equals 1 to infinity, be a sequence in X. So far, I'm not lost. Uh-oh. I see the words for convenience. Now I'm in trouble. For convenience, we rewrite the sequence in the form, what? So he says, okay, well, instead, set x sub j equal to x sub 1j, j equals 1, 2, da da da. All right, so you just put a little label on there, right? Okay, all right. I guess you can add a label.
Is that capital?
What's that? Oh, that's just, no. Use different letters. That would make it too easy to understand. No, we'll use the same letter. As to maximize the confusion. All right, very good. Then he says, by induction, we construct sequences xkj. Induction on what? K greater than or equal to 2. On k, I think you're right. X, K, J. I mean, he's about to describe what the terms and condition are for these new contraptions. All right? With the following properties. What are the properties? Number 1, xkj, j equals 1 to infinity, is a subsequence of xk minus 1 j all right, each one's a subsequence of the one. It contains the one before it as a subsequence. And what else? 2. Oh. 2. What? He says x sub k j, j equals 1 to infinity, is contained in a ball of radius 1 over k. Because it's a sequence in X. I mean, come on. I don't think that's obvious yet. I think we need to keep reading because it's. I mean, you know. All right. He says, indeed, suppose k is greater than or equal to 2, and that we already have sequences. I think we're about to make the induction step. Okay. So this is an inductive claim. Right? He's made the base case, I guess. Yeah. What's that?
No, you re-index the original sequence as the first one.
Yeah. Yeah. Let us forge ahead here. I think we're going to make an induction argument that you can construct these. I believe that's what's about to happen. All right. He says, so suppose k is greater than or equal to 2, and we already have the sequences x, I, j equals 1 to infinity for what? For I less than k. So what's he doing? Looks like a strong induction, doesn't it? Yeah. He says, let B1 through Bn be a finite number of balls of radius 1 over k that cover x. Of radius, what did I say? Why can't we do that? Oh, it's totally bounded. Yes. So, okay. Definition of totally bounded, perhaps? Okay. Then what? He says, since there are infinitely many indices j, all right, and only finitely many balls, there must exist at least one ball, say Bm, such that xk minus 1 comma j is in Bm for infinitely many j greater than or equal to 1. So there must exist at least one ball, say Bm, such that x sub k minus 1 comma j is in Bm for infinitely many j greater than or equal to 1. All right. He says, now let xk1 be the first of the xk minus 1 j's that belongs to Bm. Let xk1 be first element in this guy, which is also in Bm. Right? And he says, let xk2 be the second one that's in there, and so forth, all right? He says, then xkj has the properties 1 and 2. Oh, I must go on. Time flies when you're having fun, yes? All right, so he draws a picture now. X1, 1, X2, 1, X3, 1, and so forth. X1, 2, X1, 3, X1, 4, X2, 2, X2, 3, X2, 4, X3, 3, 2, X3, 3, X3, 4, and this goes on, of course. And what he says is, now set y sub n equal to xnn. So this sequence, yn, n equals 1 to infinity, is the diagonal sequence. And then he draws, he's like, see it? Yes, I can see it's a diagonal. Very good. Okay. That's y1, y2, y3. All right. He says it is a subsequence of the original sequence. All right. And furthermore, if we drop the first k minus 1 terms, the resulting sequence, so if we consider y sub n equals k to infinity, all right, then this is a subsequence of our original sequence, all right? And what else? What can you say about the distance from yn to ym? The distance from xnn to xmm, all right. So, but I mean, what Sam said is what he writes down. It's true. What were you saying we should do to see that? Triangle equality, xnn. Was this right or no? Mn? Oh. And then what? Should I put e plus or less than? Or distance from what? Mm. And then, yeah, I know, right?
Oh, yeah. So both of those are less than one of them. Or, yeah, less than one.
So I guess that makes this less than 2 over k? Oh, there's a 2 there. We know. And then what does that show? Well, as k goes to infinity, the distance between subsequent elements in this subsequence y sub n goes to 0, which is to say that the diagonal subsequence is Cauchy. Theorem 5.6 proved. This is not something that most of us would just do of our own accord, right? Whatever gave Cantor the insight to get to see this kind of argument is why he was able to solve problems people hadn't solved before, right? So my brother says that if you a lot of times these mathematicians, what it is, they discover this new trick, right? And all of their results are really this trick. And so they'll be very productive when they're young and they've got the trick and working. But after a while, everybody else learns the trick and they stop being so productive, right? So don't share your tricks is what I'm trying to say. Now we're past that, right? We share things freely. All right, so there you go. So if I was to have an in-class test in here, that is not something I would test. I mean, this is a deep construction that I think you really have to stop and meditate on to really get what's going on here, right? But there comes a point in your research, if you do research, where maybe this is the kind of thing you need to do, right? I don't know. I mean, I've encountered things like this. If you're trying to work on something that has the form, something like this, g of xy, and you're trying to or no, g of xx rather, and you're trying to prove things for this, sometimes it's very productive instead to look at this as g of xy such that x equals to y. It might be like introducing that new variable and looking at it in the case that they're equal somehow reveals some insight which would not be previously evident. It's kind of sort of what's going on here. Not. But anyway, maybe not. Next up, a metric space X is separable if there is a dense subset of X which is countable. Okay, so I'm actually going to just go ahead and read the rest of this section because I want to write down things about continuity, all right? And I don't want to go over time today because I'm tired. So let's see here. There's not that much more to write. All right. Oh, so lazy. Why am I so lazy? All right, let's see here. Aw, shnikes. Oh, well. All right, so definition, metric space X is separable if there exists dense subset of X that is countable. For example, if we look at the reals, right, with respect to the usual metric, right, usual distance function, and we look at, say, the subset of rational numbers, right, what's the closure of the rational numbers? Well, the closure of the rational numbers is the whole reals, right? So if the closure of a subset is the whole set, that means that that subset is dense. That's the definition of dense. So the reals are dense. Excuse me, the rationals are dense in the reals. But, hey, thanks to Cantor, we have a proof that the rational numbers are countable because you could put them in lowest terms and zigzag them out or whatever. I mean, there's an argument that proves rational numbers are countable. Don't ask me to do it. That's kind of more Sprano's thing, right? So, real numbers are separable. Woo-hoo. Theorem. A subspace of separable metric space is separable. That proof doesn't look too bad. I'm going to skip it though. And theorem 5.8 a totally bounded metric space is separable. Tote bounded X implies X separable. That proof doesn't look too bad. I should go on. Past the proof, we run into a paragraph of foreshadowing text. He says, a base of open sets for a metric space is a family script B of open subsets of X such that every open subset of X is the union of sets in the base. For instance, the family of open balls forms a base of open sets for a metric space, as does the family of open balls with rational radii. He says, theorem 4.1 shows that the family of sets of the form U1 direct product, Cartesian product UN, where Uj is open and Xj, forms a base of open sets for the product metric space X1 through Xn. All right. Lemma 5.9. We'll talk more about base in the topological context, guys. So this is a foreshadowing comment there. A family B of open subsets of metric space is a base if and only if. So what are the terms and conditions for that being a base? Again, to be a base means that you can write any open set as a union of sets in the base. All right? So here's the terms and condition necessary for a family of open sets in a metric space X being a base. The terms and conditions, according to lemma 5.9, is that for each X in the metric space big X and each open neighborhood U of X, there exists V in B such that X is contained in V and V is a subset of U. When did he define neighborhood? Okay, so I'm not alone in that. Won't you be my neighbor? Won't you be? The media hauled the widow of Rogers out so she could comment on what he'd have to say about Trump. It's like, you tactless media. Like, I understand you hate Trump, but will you go to no? Is there no end you will not go to? Like, I don't need the widow of Fred Rogers to tell me that Mr. Rogers would not approve of Trump's tact. I mean, we know this, right? He's not behaving in a neighborly way. First of all, he's got no sweater. Never seen him do anything with his shoes, much less hang up a coat. So, anyway. So I think the neighborhood here, I think if something's in this base, it's called a neighborhood. So it's saying if you pick any, no? Just an open set which contains the point. That's probably it. Oh. And A neighborhood is a set which contains the point and
I mean,
has a subset of the neighborhood, which is itself an open set around the point. Yes. All right, let us go on. So sorry. Anyway, this foreshadows, we talk about in abstract topological spaces, the notion of a base for the topology. And this is basically the definition of it. We'll come back to it, okay? And so here he says, this is a metric space satisfies the second axiom of countability, or is quote unquote second countable, if there is a base of open sets that is at most countable. In other words, X is second countable if there is a sequence of open sets such that each open set U is the union of the sets in the sequence. Theorem 5.10, a metric space is second countable if and only if it's separable. And then finally, this actually is the linchpin in completing the proof of theorem 5.1, which is a hard theorem. This is Lindelof's, I'm probably mispronouncing that theorem. Suppose a metric space X is second countable. Then every open cover of X has a countable subcover. So, and then he uses that to complete the theorem 5.1. And then finally, his last theorem in this is a compact metric space is separable and second countable. So, to me, those things are kind of technical, but worth a read. That brings us to section 6, which is on continuous functions. And so pretty much what we find in this section is the epsilon delta definition of continuity for a function, which perhaps you already know. I don't know. Do you guys know? Should I write that? Let me write it down. So F from metric space X to metric space Y is continuous at X and X, right? If whenever xn goes to X, we find f of xn. So this is the sequential definition of continuity. Theorem 6.1 says that that's equivalent to the epsilon delta definition that you might be more familiar with. So theorem 6.1 says that f from X to Y continuous at X and X if and only if for each epsilon greater than 0, right, there exists delta greater than 0 such that whenever z in X satisfies that the distance from X to Z is less than delta, then rho of f of X comma f of Z is less than epsilon. So what's going on here is that he's using d for the distance function in X, all right? And he's using rho for the distance function in the range space, the codomain. We could prove that a function is continuous at X if and only if the inverse image of any open ball, What's that? Only for, let me just, sorry, let me stay between my lines. One moment here. Oh man, son of a gun. Well, I think his theorem 6.2 is that the following are equivalent for a function from a metric space to a metric space. F is continuous. For each x and epsilon greater than 0, there exists delta such that whenever z is an x, it satisfies the distance between x and z is less than delta. That implies that the distance from f of x to f of z is less than epsilon. And then 6.3, which is what I was trying to say badly a second ago, is that the inverse image of v is an open subset of x for every open subset of y, every open subset v of y. So this theorem 6.2 foreshadows the topological definition of continuity. In topological spaces, we're just going to take 6.3 as the definition for continuity. So the fact, like that ends up being the definition for topology. If you have a map from one topological space to another, it's continuous if and only if the inverse image of open sets is open. That becomes our definition of continuous. But of course, it's a consequence here of other things. And finally, theorem 6.3 is, of course, interesting. It says x and y metric spaces, x compact, then every continuous function from f, continuous function f from x to y is uniformly continuous. But I said we'd talk about uniform continuity some other day, so that's not today. So next up is normed linear spaces and the contraction mapping principle. And I might say a word or two about Fauché derivatives. So this is part of what I thought this book was really neat in that it talks about these things. Not every topology book talks about that part of analysis, but it seems appropriate to me to talk about that at least some in this course. So I think what's coming has less application, as far as I can think of, to abstract topology. But maybe that's just because I don't know enough abstract topology. There are, after all, fixed point theorems in abstract topology, which are interesting. But yeah, Brouwer's fixed point theorem, for example.